Okay, here we are. We're just going to review inorganic nomenclature today. I'm assuming that we've gone over at some point how to figure out the formula for compounds. And so I'm just going to go over this with you, how to name binary ionic compounds. Okay, binary, what do we mean by binary? Well, binary is two. So we're talking two elements only in the compound for today. Binary ionic compounds. And what do we mean by ionic? Well, you're well aware now that our definition that we're going to use is metal and bonded to a non-metal. Okay, it doesn't work every single time, but for 99.9% of the time, it works great. Okay, I'm also going to suggest perhaps that maybe it would be a good idea that you sort of think in terms of nomenclature, in terms of a bit of a decision tree. If we have a compound that we want to name, the first thing you're going to ask is the compound ionic or is it covalent? And that's a very easy answer to arrive at. If it's a metal, which I'll designate here as M, and a non-metal, I'm going to have ionic, and in this case I'll go off to the left. If it's non-metal and a non-metal, NM, NM, I'll go off here to the right. Now, if we go on to the ionic side, we have one more decision that's got to be made, okay? And that decision is which system do we use to name that compound. Now, here we have to look just at the metal. Don't get confused with the non-metal, especially when you get into the chlorine and bromine, iodine, that kind of thing. We're going to ask if the metal is the metal multivalent. Or we could say, does it have more than one oxidation state? So you're probably familiar now with this periodic table. I've given you a copy of this, and if we look down in this corner, it's this little number above the element that we're interested in. And if you look at the key, it says it's an oxidation state, and I'll explain that in a few days when we talk about redox chemistry. But this periodic table is great. It gives you all the oxidation states or all the valences. So is the metal multivalent? We're going to ask that question. And if the answer is no, you're going to use a simple system to name. Okay. And if the answer is yes, then we're going to use something called the Stock system, named after Alfred Stock, who I'm sure was a German chemist at one time. And of course, if we've gone to the covalent side, okay, if we're on the covalent side, you might recall that there you use the prefix system. And that's kind of fun, and it's a fairly simple system. The Stock system, by the way, if you remember, it uses the Roman numerals. Okay, so let's just go through a couple of examples here. I'm just going to flip the page to page 76 for now, and we'll take a look at what happens there. So I'll just drag this down, and so the simple system, you're only going to use those elements that have a single individual valence or oxidation state. So on our periodic table, you can see that certainly the group 1 ions, lithium to francium, make use of that one valence. They're all +1. The group headed by beryllium is all going to be +2. Beryllium, magnesium, calcium, all +2. They only have the one value. Scandium +3, yttrium +3, lanthanum. Same thing. If I move over here, we've got aluminum and gallium and indium. Silver only has one. So these are the elements that you're going to be using the simple system of nomenclature. And then farther down, I've given you a table. I see that it's got a little bit out of order here in terms of its formatting, but we have this little table here. So the simple system, basically you just follow the metal name with the root of the non-metal name, and then you end it in IDE. Okay, so we have hydride, carbide, silicide. Now the ones that you'll see most often obviously are oxide, fluoride, chloride, sometimes sulfides, and I'll put in bromide and iodide, but we're not going to see too many selenides and tellurides, arsenide, that kind of thing. We won't see too many of those. So these are the main ones that you will see. Now there are two polyatomic ions that also end in IDE, and that's hydroxide, which we see a whole lot, and cyanide, which I hope you never see because it's quite dangerous. It can really mess you up if you're in the neighborhood of cyanides. Okay, now how do we do this? How are we going to name something? Well, let's take a fairly simple compound. Let's try something like we'll take potassium and combine it with fluoride, and so we would say, well, it's potassium fluoride, because potassium only has the one valence or oxidation state, and so we can use the simple system, and so we would call it potassium fluoride. If we took, let's say, calcium and combined it with nitrogen, well, that's kind of an unusual compound, but it would be Ca3N2. We would see that calcium has only the one oxidation state, so it's calcium nitride. So that's a fairly simple way to get our nomenclature in the simple system. Okay, now let's, whoops, I just missed a page there. So let's move on. How do we name compounds where the metals have more than one valence or oxidation state? And again, if we go back to our periodic table, we can see that we're talking mainly elements that are in the transition series. Okay, so titanium has several, vanadium has quite a number, and chromium is plus 6, 3, and 2, and manganese has a whole pile of them, 7, 6, 4, 3, 2. Iron has got 2, 2, and 3, cobalt 2 and 3, nickel 2 and 3, copper 1 and 2, and so these are elements that we have a bit of a problem with. For instance, if we looked at iron, for instance, a very common element, if I took iron 2 plus and combined it with oxygen, which is 2 minus, my compound would be FeO, which I believe is a black solid. Okay. If I take iron, I just want to make sure I'm still on the page here, Fe3 plus and combine it with oxygen 2 minus, I would get the compound Fe2O3, a precursor to rust, and we would get a red solid on this one. So obviously different compounds, and if I went and asked you to go get some iron oxide, you wouldn't know which one to bring back. So we can't use the simple system for elements where the metal has more than one valence. We have to come up with another system. And in your notes, you'll see that it was named after Alfred Stock. Okay, there he is. There are his dates. And it was used for binary compounds where the metal ion has more than one valence. Okay, so if we go again, here's just a reminder that if we look at your periodic table, just above the element, you'll see either a single digit or you'll see multiple digits. Okay, and if it's multiple digits, then we're going to have to use the stock system. If it's a single digit, we can use a simple system. So you're going to write the name, and the instructions are here. When we're naming compounds using the stock system, you write the name of the metal followed, and that's without a space if you want to do it correctly, by the numerical value of the charge, which is in a Roman numeral, and that's in a parenthesis. And then you write the name of the nonmetal. Okay, now can we please remember, I can't emphasize this enough because every year there's a couple students that forget to do this. The Roman numeral is the charge of the positive metal ion. Okay, I get lots of students that use either the non-metal or I don't know where they get their numbers sometimes. So if we were to go back to our example, FeO, I knew that the iron was 2 plus and the oxygen 2 minus. I would call this iron 2 oxide. And my other example, Fe2O3, is iron 3 oxide. Okay, let's maybe go through a couple more examples. If I have a compound CuCl2, I would look at the chlorine and say, well, in my binary ionic compounds, chlorine is always going to be -1. Now I know you see that there are other oxidation states above chlorine, but in a binary compound, chlorine's always going to be -1. Okay, so if I have two negative charges, that means the charge on the copper must be 2+. So I would say this is copper 2 chloride. Okay, let's try a slightly tougher one. Say I gave you this compound, MnO2, a nice brown solid that sometimes is found in I don't know, water well systems and stuff like that. Anyway, if I look at this one, I would look at, I can't do the reverse crisscross to get the charge on the ion. So again, oxygen is 2- in a binary system. So I have 2 of them. So I have 4 negative charges. That means that the charge on the manganese must be 4+. And when I go look at manganese, it's got a whole host of oxidation states, 7, 6, 4, 2, and 3. So I have to call this, using the stock system, manganese 4 oxide. Okay, that's the both the simple and the stock system for naming binary ionic compounds. You'll see the homework will be with the on-call sheet. However, if you're looking for it, it's on pages 78 and 79 of your notes. If you could do those 2 sheets for next day, you won't get too far behind. And let me know if you're having any problems. Thanks a lot.